background of my work is based on the application of foam in microfluidic channel. So this is one of the example of foam improved oil recovery. So we in this process we inject foam into the oil reservoir where there is pores in it, and the pores create really tiny channels, size of micron, just such a microfluidic channel, and so the foam inside the channel will displace the oil, and then the oil will be pushed out of the pores, and then can be collected on the other side of the reservoir. So this method improves the amount of oil can be extracted from the reservoir, but there is a problem. So the size of the bubbles and the flow behavior of the foam inside the channels affect the efficiency of the extraction of the oil. So we want to know what kind of process which is more effective, and what kind of conditions which is good for the operation of this system. So we try to develop a model on the bubble dynamics inside the microfluidic channel. So first we need to develop the appropriate model for the foam flow, and after we have the model, we want to examine the effect of the driving velocity, the bubble size, the constriction size, and the liquid fraction in the rearrangement and of the bubble passing through the channel with constriction. So this is the example of the case. There are three possible behavior of the bubbles when it passes through a constriction. First is there won't be any change, so it's just keeping the shape, and also it can be reorientation or pinch off when the bubble is break up into smaller bubbles. So this is our setup. So we construct a channel with this shape. It's a straight channel with a constriction, and this is a 90-degree angle, and we vary the size of the constriction and also the velocity of the bubble when they move, and also the size of the bubble. And maybe it's not very obvious here, we vary the liquid fraction, and we do the simulation using this method. So we look at a case of so we look at a case of two-dimensional foam. It's basically one layer of bubble confined between two flat plates, just like this. And this is the view from above, and this is also the view from above of the channel. And so we use a software called Surface Evolver. It's a software dedicated for foam optimization, and we in the simulation we divide the surface of the bubbles here into small edges, and we calculate the movement of the edges based on the force balance of this one. So the balance is between the viscous drag in this one and the pressure gradient between the inside of the bubble and the liquid in the film, the curvature and the surface tension. So the bubble created using surfactant, and it creates the gradient of surface tension, and also the curvature, which basically how much the surface of the bubble bends. And this one is the disjoining force, which determine how much one bubble separates from the other. And so this is the phenomena we have. First is there is no change of the foam structure. So just keep the shape, and this is the example when the bubble is reoriented, but there is no pinch off, so the bubble just keep its initial size. And the last one is when there is pinch off. So after certain time, the bubble will break up into smaller bubbles, and so it will keep breaking up because the pinch off happened because when the bubble is moving and then it's so squeezed, it will create a really thin neck, and then when the neck is so thin, then it will break up into a smaller bubble. And so from that, we try to summarize what is going on from one condition to the other. So here, hopefully you can see clearly from behind, we do different variation. So the x coordinate showing the capillary number, which is basically representing how fast the bubble is moving inside the channel, and the y coordinate is showing the bubble size. And so this graph representing different conditions. So this and this column is so the column is showing different liquid fraction, and the row is showing the different size of the gap. And for example, here for a small bubble, we can see that there is a situation when the velocity is really low, then most likely it will only be there is no change or just reorientation. But with higher velocity, then it starts to get pinch off. So the pinch off is more likely happen when the velocity is quite fast. And can see so this way the size of the bubble is getting larger when so when we have the larger bubble, the chance of reorientation is greater. So for example, here with a small bubble, there is only reorientation only happen 2 times here, but with the larger bubble, the reorientation happen 4 times. I mean, in 4 different conditions. So from here, we draw a conclusion that the model that we use can simulate the bubble dynamics, showing the pinch off and reorientation in the channel. And the reorientation is more likely to occur when the bubble is large, and the pinch off is more likely to occur at high velocity or the high capillary number. And with the larger gap of the constriction, the likelihood of the reorientation and pinch off decreases, and also with the increasing liquid fraction, and also the and also happen with the increasing liquid fraction. So last, I'd like to thank for you to listening, and also I'll thank to my sponsors. Thank you.
Thank you. Any questions? Yeah, Andrew.
Did you have to put in a specific criterion for the pinch off in your model?
Yes. So for the pinch off, after the bubble forming a neck like this, when the neck reaching a certain size, then the pinch off will happen. Okay. Thanks.
There's another one there.
My question have a preferred distribution?
So when it's reoriented, and what we do here is we use so we use a periodic boundary where everything live here will come back here. So
Okay,
it just
so it doesn't
kind
have
of
very
going
long-
round and round, and what happened is just keep keeping that orientation when it's reorienting.
And how important is the 90 degrees angle? If you change that angle, would you get different effects?
Okay, so the reason we choose 90-degree angle because we want to compare the simulation with experiments. So the experiment which done now is using 90-degree angle, but I think it will be interesting to observe what the effect of the angle of the constriction later on.
Okay, thank you very much.
Thanks.
So what you see here is a sketch of an experiment which brought us into this field. And it started with a collaboration with people from the nano and micro materials department who were trying to make wonderful new solar cells by depositing their concoctions in the form of thin films and then letting it dry. And what they observe is that they get sort of drying fronts which come in from the edge over here. So this is, in a sense, a paradigmatic experiment which consists of some latex beads, for example, immersed into a volatile substance. And as the material evaporates from the edges, preferably, you get this porous medium-like zone where the material has compacted into a solid material. Here you still have the suspension more or less mobile, and as liquid evaporates and gets sucked into the porous medium, you have a zone where there's an aggregation going on and a jamming. So the mobile suspension turns into something that is solid. And that caught our attention. We said, well, let's see whether we can do something modeling-wise here. So we looked at dense suspension, so of n identical particles, all of them in a range where they are non-Brownian. You can characterize this by essentially a volume fraction of the volume of the particles compared to the total volume. And as you know, there is a limit to which you can pack spheres. And when you get close to this volume fraction, which is around 60%, the spheres touch, motion gets very difficult, and the viscosity diverges, so you get this kind of jamming-like behavior. Now, suspension models have been around for a while. Most of them have these basic laws, so a no void condition that the two volume fractions have to add up. And for each of the volume fractions, solid and liquid, you have a mass conservation law where things start to diverge, is how you write down the momentum equation. So one way of doing this, and this is probably the oldest one, is through drift flux models where you have you split the velocity in a volumetric average, which gives the background flow, for example, in a pipe, and a drift term, which measures the drift of the suspensions relative to the background velocity. And for this, you write down these drift flux equations, and they have an interesting feature, namely that the particles try to migrate in the direction of the larger strain. So this is how these models were put together semi-empirically by Leighton and Akrivos, and then there was a whole string of research on them. And it turns out they capture the migration towards the middle quite well, but they also produce a singularity in the middle where you get a peak in the volume fraction, which is not exactly what you see in the experiment. You see the migration, but you more or less see a flattened plug region in the middle of the pipe flow. So other ingredients are the stress-strain relations. So for example, the Einstein relation for dilute suspensions, or the Krieger and the Hertie relation for very dense suspensions. And here you already see the singular behavior and the viscosity as phi goes to phi s c. And when you're at the extreme, when things are already solid, then you still have a percolation of the liquid, and that is governed by Darcy's law. So that's one limiting behavior you might want to capture. Okay, jamming is an unresolved problem, I would say, and a one that is still attracting the minds of very, very smart people. One of the big breakthroughs paralleled the talk we had this morning or earlier this morning on granular flows, where you established the importance of the friction-driven rheology, and in particular it turned out and was postulated by scaling arguments that the friction should depend on a single parameter, the viscous number, which is the corresponding thing to the inertial number we saw in Tom's talk. So this is the ratio of viscous stresses compared to the confining pressure acting on these particles. This relation was then verified experimentally by Boyer and also Olivier, who is one of our plenary speakers here. And it turns out you can then, all the data collapses nicely as predicted, and from the data you can then extract a relation and turn it into a more conventional expression for the viscosity. So this you can then use in a proper multi-phase model. So how do you construct multi-phase models? Well, there's one way goes back to Drew and Passmann. You write down the microscopic mass and momentum conservation laws and the conditions at the interfaces. You average them to get an average set of equations for the mass conservation and momentum conservations. And notice here these terms, which are unusual if you come from a single-phase rheology. These are the drag terms where the two phases exchange momentum. And there is a well-established empirical law going back to Cosini-Kármán, which is basically a generalization of the flow in a porous medium. The liquid phase will be modeled as Newtonian, and the solid phase is then described by the law we took from Boyer's paper. So you have two relations for the stresses and the confining pressure. And what you notice is that eta S and eta N, the two viscosities, have singularities of the same order. So what does this mean? Let's assume you keep PC fixed and you let gamma S dot, the strain rate, go to 0. Then eta N has to go to infinity. Phi S has to go to phi SC. But this also means that eta S goes to infinity at the same rate. So if you look at this product here and take the modulus, it will have to go to a fixed value. So gamma S dot goes to 0, stress goes to a fixed value, bingo, we have a yield stress behavior. So once you're below this limiting value, gamma S dot is 0, and you have a solid phase, basically. The solid phase behaves like a solid. Okay, so plug this all in, non-dimensionalize. This parameter here I will return to, which is the Darcy number. It's a ratio of the geometric macroscopic sizes compared to the microscopic sizes, so it's usually a large number. We have this yield stress behavior. We anticipate that, so the easiest case where you might see this pan out is in Poiseuille flow, where you have a zero strain rate in the middle. So you have this geometry. You write down the simplified equations for this specific flow. With some algebra, you can reduce it to an equation just for the solid fraction and the drift velocity W. And you see there are two regions. And it turns out only if you have two regions, an unyielded region in the middle, you can actually find a solution through a phase-space discussion. And it turns out that these are exactly the unique solutions you get in this situation. So at the walls, the particle fraction is relatively low, but it increases towards the middle until it hits the critical value, and there it plateaus. And if you look at the velocities, you get this nice plug-like flow behavior. So that looks all nice. And you can extend this a bit further into the dynamic regime and show that you can formulate a drift flux model plus this jamming region. So what you do is you do an expansion in the large Darcy number. You get this diffusion equation, nonlinear diffusion equation. If you solve it starting with a flat state, the concentration jumps up to the critical state and then expands until you get the equilibrium value. Stability is another thing you might want to look at, and that's where things get really interesting. We started actually with a simpler flow, the Couette flow that you would use, for example, in a rheometer, which has a very simple homogeneous base state. You perturb around this base state, calculate the eigenvalues, and what you see is that in certain parameter ranges, which are relevant in the experiments, the growth rate goes to infinity, as the wave number goes to infinity. So we have this ill-posedness, which is probably very closely related to the case you have in granular flows. Beyond that, there's also an instability, a convective instability, which is much more benign and acts on a transient scale, but together with nonlinearities, it might actually yield a visible instability. And I would like to end my talk with a remark. You have this yield stress behavior, which puts this liquid somehow in a relation to Bingham-type flows, but the instabilities are very peculiar for the suspension. So none of this happens in Bingham flows. Bingham flows in a pipe, for example, are linearly stable. Okay, thank you very much for your attention.
I wasn't sure why you had, if I understood it correctly, a no slip condition for the solid phase. I don't see why the solid phase, there could not be a velocity discontinuity at the bottom.
That's true. We haven't tried that. So it was one choice we made at that point, that this would just stick there. Yeah, it would be an extension.
This convective instability that you see, is this similar to like Kelvin wave vector stretching?
Yes, I think so. That's at least the theory where we placed it in, but we haven't. We observed it mathematically and put it in roughly in that box, but we haven't observed it. It would really be nice to find an analogy there. So yeah, sounds familiar at least.
Do you see a sign of the instability when you model the Poisson flow?
What do you mean with sign?
In your simulation, something going wrong?
We haven't done. So the student who did this, which was Tobias, he tried to do simulations for these models, and he got stuck. But there are people who are successfully doing simulations. Or the model always seems to be slightly modified. So maybe they took out the ill-posedness. So that is an interesting question. We stopped there, yeah. So it's not where the research should stop, of course.
Okay, thank you very much.
Thank you very much. My name's Liam. I'm from UCL. I work under Professor Helen Wilson, who I'm sure many of you will have the pleasure of meeting. I hope to live up to her very high reputation, which is an unfortunate coincidence for me. I'm going to talk today about the rheological properties with solid sphere suspensions in second-order fluid with the use of this single-cell model. Now, first of all, I should probably say why suspensions are important. In day-to-day life, they can be seen in such things as toothpastes, creams, general health products, gels, this sort of thing. And they can also aid with manufacturing, processing, engineering, and things of this nature. So, on a very, very basic diagram, I have a box, let's call it an infinite box, with a series of perfectly spherical solid particles homogeneously dispersed within them. And this has been studied for many, many years and is very, very nice in the literature. What we decide to do at this point is to add in what I would like to put forward as the best animation of the talk so far. Yes, look at that. You see, can you spot the difference? So the blue sphere around each of these particles is contains a finite amount of fluid in the background fluid, which we take to be second-order fluid. I'll describe it a bit later. Each cell around each particle has the same amount of finite fluid, so in that sense they're all identical. And they have a few properties. We enforce that no particle may collide with another particle, and we also enforce that no fluid that is, for instance, within this cell may coincide with fluid that's in this cell. So if two cells were to touch, they would touch at exactly one point on what I like to call the sphere of influence. The point of this really is to try and derive down the line some concentration-dependent properties, such as viscosity and other material functions to do with second-order fluid using this cell. So I enforce a background flow. We're going to make it general and steady as much as possible, but also linear. So it depends on the velocity gradient at some distance, infinity, let's call it. And you see I've just split that velocity gradient into the sum of the rate of strain tensor and the rotational tensor. Since none of the fluid outside any of the cells can be affected by the particles, that's the key point, the velocity at the boundary of a cell at the sphere of influence must mirror the velocity at infinity. And so we have a boundary condition for the cell. Now, all cells are identical, so we say that if we can solve the flow within one cell, then we can solve it within all of the cells. They're just identical. We've ensured that the particle will be force-free because I've included no translational velocity of any kind. And to ensure a torque-free particle as well, we simply match the rotational component of the velocity at the surface of the sphere. So if you can imagine, say, the sphere is rotating, the solid sphere is rotating, then the cell will rotate at the same rate. You'll get no rotational velocity inside. The second-order fluid equations. They look a bit like this. You have your classic incompressibility. I apologize for the index notation. It just works better for me. It's inertialess. This is a momentum balance. It comes directly from Navier-Stokes under negligible Reynolds number. We have a stress tensor, which is your classic Newtonian stress tensor, plus this extra sigma ij star, which is your extra polymeric stress, the non-Newtonian part of the stress. Which is where the second order part comes in. Now, this equation, alpha naught Aij here is a second order Rivlin-Eriksson tensor. What you need to know about that, basically, is that it behaves like the rate of strain squared, plus this rate of strain, dot rate of strain term over here. Alpha naught and alpha 1 are material parameters that depend on the zero shear normal stress components. Eta naught is our solvent viscosity, so constant solvent viscosity, I'm assuming. This can be non-dimensionalized into the following equation, which depends on the Weisenberg number and this material property epsilon, which is simply a ratio of my other two material properties. Now, the most important quantity for me specifically is the bulk stress, which is an average, an ensemble average of the stress within the entire fluid. So not just within the cell, but within the fluid outside of any of the cells suspended in the suspension. In the absence of particles entirely, sorry, I forgot to mention. With this stress equation, what we can do is apply a perturbation series around the Weisenberg number. So if we assume that the Weisenberg number is small, then at order 1, the stress will simply be the Newtonian stress, and we get out Stokes' set of equations. And at order 1, what we find is that the average stress within a suspension without any spheres, so no solid phase, is simply what you'd expect it to be, 2 EIJB times the solvent viscosity. The pressure has been removed because it's an isotropic term. However, as soon as we include some solid spheres into the mix, we find that under this ensemble average, we get this extra 1 plus term, which is highly convenient and inconvenient at the same time, multiplied by this linear term in the concentration, and again multiplied by this rate of strain. Now, the really convenient thing is that these two equations are very, very similar in that this second ensemble average stress is simply the first one, but instead of this eta naught term, we have an effective viscosity, which I will determine to be eta naught times this big long bracket. The big long bracket makes a bit of sense. The properties you would expect under the limits b tend to 1 and b tend to infinity are that the effective viscosity, is that the bulk stress blows up as b tends to 1, so that's where you have your outer sphere of influence getting closer and closer to the sphere, so it becomes less and less gap for which the fluid can react to the change in velocity. So you expect it to blow up there, and as b tends to infinity, you get the case where there's simply one sphere in an infinite domain of fluid which can all be affected by this one cell, which, thankfully, the previous speaker has already said is Einstein's relation. And as b tends to infinity, we do get that 10 over 4 to be the dominant term, and we get 1 plus phi over 2 phi. However, this sphere of influence isn't very helpful, like physically, because it doesn't actually exist. There's no, plastic sphere in the suspension. It's just a point in space, and it's not very useful. We can't measure it, and all of this, these sort of reasons. So what we do is say, okay, well, we know that Krieger-Doherty works. It's nice. It has the same limits under phi tends to 0 and phi tends to the maximum packing fraction, which I take to be 0.64, some say 0.63. Let's leave that as it is. And in that case, what I do is simply say, okay, what value does B have to be to match these two viscosities at all concentrations? And it turns out we get this rather unfortunately blurry curve. The solid black line is the B of phi, and it has the properties we desire. At 0.64 maximum packing, B becomes 1. Remember, that's when the viscosity blows up. And as the concentration tends to 0, we get that B tends to infinity. And trust me, it does tend to infinity. Okay, so that's at Newtonian order. What about if we move up to Weisenberg order? Things become a bit more complicated, but in essence, they have the same sort of properties. In the absence of spheres, the bulk stress becomes this combination of constant tensor terms multiplied by material parameters. It's not too much to worry about. But what you should know is that the bulk stress term with spheres actually follows the same pattern, except we have a different material parameter in front of each term. So what we do is say, okay, these are the effective terms, much like we did with the effective viscosity. What they will analytically depend on B, the point of the sphere of influence, but using our matching to Krieger-Doherty, we can substitute out that B for a dependence on the concentration. And so everything now depends on this concentration and this ratio of material parameters, epsilon. And just for a clue as to what they look like, the analytical alpha naught bar, which is the suspension value of this material parameter, it actually is exactly the effective viscosity, which can be proven is correct. And alpha 1 is a little bit more complicated, has the same sort of curve structure, but has some epsilon dependence, which appears to diverge quicker as epsilon gets closer and closer to 0. And that's it. Thank you for listening. Any questions?
So can I ask,
of course.
So presumably somewhere in here is the first normal stress difference. Is that
Mm-hmm.
is that in your alpha 1 then? Is that?
Yes. So there are two ways of looking at it. You can either define it in terms of alpha naught and alpha 1, and from there get the first normal stress difference, or you can define the alpha naught and alpha 1 in terms of the first normal stress differences. It's a linear combination of alpha naught and alpha 1. Can't remember quite what it is. I think it might be alpha naught minus alpha 1 over 4. Something around about that. But yes, it's fully derivable. Yeah, and easy.
So I guess my question was then, what's the effect of the particles on the ratio of the normal stresses, or do they stay the same as the background fluid?
They don't.
Right.
It becomes a little bit more complicated, and there's a change of sign of second normal stress difference, which is interesting, but I haven't quite got my hand around it, so I haven't presented it.
Because I think that fits with what happens in experiments. And I think experimentally, if you add particles, you change the second normal stress difference sign. So it does look like your theory is doing some nice effects.
That would be highly useful. Thank you.
Okay, thanks for the introduction. Thank you everyone for attending this talk. My name's Henry. My co-workers are Andrew Corker and David Dennis, Eduardo Saiz from Imperial, and Esther Garcia-Tunon and Rob Poole. And I'll be talking about capillary breakup extensional rheometry measurements in graphene oxide suspensions. So a brief overview, will be a quick introduction about what graphene oxide is, and then what the KBER technique's about, a quick run at experimental methods, a validation on a Newtonian test case, and then some results from sort of low concentration graphene oxide colloids or solutions, and then conclusions and outlook. Okay, so what's graphene oxide? Graphene oxide, or GO, is a chemically oxidized sheet of graphene. Okay, so we've got a little schematic of it up here. And what makes it special is it's a two-dimensional flake with these oxygen functional groups that are attached to it, and some unoxidized bits which are just still graphene or graphite. So it's amphiphilic in nature, and it's also, so it's these sort of oxidized and unoxidized bits which give graphene oxide its unique rheological properties. Here we've got an image from an optical microscope, and you can see that it's actually just a flat flake. It can range in size. There's a scale bar here of 25 microns. So these flakes are actually highly anisotropic. They can range in length from 25 to 100 microns, but have an aspect ratio. So they're non-uniform, essentially. They're not homogeneous in geometry. And they also have a size distribution, which is during the manufacturing process, it's quite hard to control the size of the flakes themselves. So it has numerous applications, biomedical, electrical, and materials engineering, but our application of interest is actually in processing. So we've got a little 3D print. So we've got additive manufacturing using graphene oxides. We've got a 3D printer. The colloids of GO behave as multifunctional additives which aid in 3D printing processes. Right here we're actually printing just graphene oxide, but at low concentrations. So this is at a concentration of probably about 3 volume%. At much lower concentrations, you can add it to things like ceramics or aluminium oxides and make them printable when they would otherwise be not printable. The shear rheology of GO is well known, so Delgucci and Shen and Garcia-Tunon 2017, but much less is known about, or much less has been reported about its extensional properties. So in this sort of flow, we've got shear near the walls and the nozzle, but extension in the center. So that's kind of what motivated this work. Okay, so what is KBER, capillary breakup extensomeometry? We probe the properties of fluids under uniaxial extension, so there's no shear. You load the fluid between two parallel plates and you move them apart so that they'll form an unstable filament which necks down or decreases in diameter with time. And from tracking the time evolution of the filament diameter, we can yield fluid extensional properties if you have a constitutional model of the type of fluid. Okay, so our methods, we used a commercial Thermo Hacker Cable 1 device equipped with 4mm end plates. And instead of relying on the laser micrometer to measure the filament evolution, we used a high-speed camera which was backlit. So we produce essentially shadowgraphs of the filaments. So standard KBER protocol, typically you apply a step strain, but at these low volume concentrations of GO, we weren't able to form filaments. So you can see that basically the filament breaks before the cessation of the movement of the top piston. So we went for what is called the slow retraction method, which was outlined by Campodino and Clausen. So essentially here, we load the sample and then manually move the end plates apart very slowly so that the filament is on, or the sample is at the edge of its static stability limit. Then we apply a very low velocity to initiate the breakup process. So that was our protocol. The methodology, so the validation was done on a glycerol water solution, which we measured in a shear rheometer of 384 millipascal seconds. We chose this high viscosity so that the timescales would be much slower. This is the raw image from the camera. We binarize it, and then we use basically in-house algorithms in MATLAB to track the interface. From that interface, we can get the diameter over time, so the time evolution. Okay, so for Newtonian cases, in the absence of inertia, essentially you have capillarity balanced by viscosity, which is described by this similarity solution of Papageorgiou, where sigma is the surface tension and mu is the viscosity. Time goes negative towards zero, so increases towards zero, so we actually normalize everything on the breakup time. And what we find is that if we take the gradient here, we can back out our viscosity, which we get to within 10% of what we measure on a shear rheometer. So we think our technique works fairly well. Very, very late in the process, inertia becomes important again. So you get this inertio-viscous regime, which was described by Eggers. It has a different front factor, but has the same functional form, so still linear. We're not able, with our temporal and spatial resolution of our imaging, we can't get to this regime, but we can certainly capture this sort of viscous regime by Papageorgiou. We tried it for a more dilute glycerol solution, so the timescale's faster, so you can see the acceleration, and then we still collapse onto this viscous regime. So we think that at least in terms of validation, we've done a pretty good job, or at least our system works fairly well. Okay, so move on to results. So I'll just show some images. So this is, just bear in mind, this is a very low volume concentration, so 0.05% volume concentration. Graphene oxide, the solvent is water. And so you can see, so this is a binarized image. The breakup process, you get this sort of right before breakup, you have this sort of near cylindrical filament before the instability sets in, and then you get a pinch off. So this is very qualitatively very Newtonian-like. We move on to our next concentration, which is just 0.1%. We see we have a very similar sort of behavior. However, the droplet pinch-off, the droplet itself is smaller, and there's a very, very sort of minor conical tapering right before the pinch-off. Okay, so we're starting to get, so only for a very small change in volume, in the concentration of the GO, we start getting quite noticeable changes in the qualitative behavior. When we go to 0.2, which is the third column here, we can see that the viscosity is increased, so the timescales slow down a bit, but essentially, hopefully we can pick out that before breakup, the filament is not, is tapered. So there's a conical taper, and it's not like a straight edge filament. So we're moving away from Newtonian-like behavior, and we get to 0.3. So this is all still very dilute in a sense. You can see that, again, this conical tapering takes over. And the breakup actually doesn't happen at mid-filament as you would see in a Newtonian flow. Okay, so hopefully you can see that I think this one breaks close to the sort of bottom third here. So this, we think, might be due to local concentration fluctuations, and it also may be down to the nature of the graphene oxide flakes being anisotropic. So it's not like it's not spheres held in solution. So there may be something going on there, but we haven't quite resolved that yet. In terms of qualitatively, if we track the diameter at very low concentration, we see that it basically follows this sort of linear regime. Because the solvent is water, the timescales are very fast, so there's probably some uncertainties right at breakup because we're not able to capture it. But we can see that it has this sort of linear behavior. There's some spread in the data, which we think is due to the nature of the flakes themselves. When we go to 0.1, we can actually see that neither a linear distribution or like a power law fit describes the data very well. But when we go to 0.2, we see the emergence of a power law behavior. The power law exponent that we backed out here is about 0.5. So, it's shear thinning essentially. And by 0.3, we have a strong power law behavior as well, and this exponent remains close to 0.5. So for these dilute concentrations, geocolloids display Newtonian-like extensional behavior, and we see the emergence of power law behavior as low as 0.2 volume percent. Okay, so over a very small concentration change, we are seeing that actually we get quite a change in the behavior of the fluid. And this transition to sort of shear thinning behavior is consistent with a shear rheology. So at small amplitude shear rheology tests, they are quite difficult to repeat for these low concentrations because essentially it's Newtonian. And the outlook is essentially, okay, can we extract elongational properties closer to printability? So we're about an order of magnitude away, but printable sort of geo at 3 volume percent is much more like a yield stress material. And so whether or not we need to develop a new sort of protocol to actually even load this material into the KBA is something that we're currently working on. And so that's it.
Any questions?
So I'm wondering what's the relevance of the oxide bit as opposed to just having graphene flakes? Does it affect urology, or is it just so you can get it in suspension?
Well, I think it does affect urology. As far as I know, graphene is hydrophobic, so that it's actually quite difficult to get into suspension. So the oxidization of the graphene actually changes the properties significantly.
Yeah.
So when you look at these graphene sheets, are they actually like one layer of the graphene structure, or are they multiple layers? Because I'm wondering, when you oxidize the surface, what happens then to the graphene structure?
So that image that we showed was obviously very dilute, so we try to isolate individual flakes, but when they're in solution, they can form sort of lattice-like structures depending on what the deformation is, I think.
No, my question was, how thin is the individual flake in
How,
number of atomic layers?
I'm not able to answer that, so I didn't work on the production of the actual graphene oxide. Sorry.
I think it's typically 2 or 3. Right. Okay, thank you very much.
Thanks.
Hi everyone, my name is Adila Azhar. Today I'm going to give you presentations about about modeling the behavior of the roly-poly fluid through a hyperbolic contractions using the open foam. Right. Polymeric item, typically plastic, are commonly used in our daily life. Different polymer items possess different behaviors. So it's which most of it can be described mathematically using constitutive, non-constitutive equations, which has been developed by the previous researchers with a relevance theory. Understanding the polymeric fluid behavior is very important in a polymer industrial processing because by understanding its behavior, we can control the flow motions, and we can also reduce the polymeric wastage and thus improve the polymer processing. Right, a set of governing equation is required here, and the governing equations for incompressible viscoelastic fluid flow can be described as follows. Consists of conservations of mass as well as the conservations of momentum, where this conservation of momentum is actually just the extensions of the Navier-Stokes equations with the additional stress tensor contributions, polymeric stress tensor the right, which depends on what type of the constitutive equations that we choose. So in my case, I'm going to look at the constitutive model, which is derived based on the simplifications of the polymer tube theory, which is known as the Rose linear entangled polymer, or in short is roly-poly model. So speaking about the polymer melts model, we can visualize the polymer melt as being analogous to a plate of a spaghetti, where the spaghetti represents the polymer chain, and each of these chain is represented by a tube which made up by neighboring chains. Right. Doi and Edward apply the Reptations model to describe the motions of the tube, the motions of the polymer chain in the tube, which until the chain is allowed to diffuse out of the tube. As we can see from here, this is the tube model, which represents each of the polymer chains in the polymer melt, and this is the single reptations, which show the motions of the polymer chain to diffuse out of the tube. Right. So the full descriptions of the roly-poly constitutive equations is described in equation 3 here, where we have the stretching term in there, and that there are two important relaxation modes here, which is the first one is the Reptations relaxation time, which the longest relaxation times govern the motions the chain reorientation, and the second one is the stretch relaxation time, which the longest relaxation times govern the retractions process, or the motions of the back and forth of the chain, or the spring-like fluctuations of the chain. Right. Before we proceed further, just to give you the idea about how the rheological behavior of the roly-poly model is, so in figure 2 here, imagine that we have 3 polymer chains that are entangled to each other. By imposing a shear rate, we can see that our chains is reoriented, and imposing higher enough shear rate, what happens is that our polymer chain will start to align and thus stretch. Translating this figure 2 into a graph here by knowing the stretch relaxation time as well as the rotations relaxation time, we can divide the behavior of the roly-poly model in 3 different regimes. The first one is the slow regime, where it behaves like a Newtonian-like behavior, while the second one is the intermediate regime, which showing the shear thinning behavior, and the last one is the fast regime, where we start to observe where the polymers start to stretch. Right. So what we did is that we implement the equation 3 just now, the roly-poly model, within the OpenFOAM software, where we can just translate the complex mathematical model just now in a high-level code in a high-level code C++ in OpenFOAM, and we use the RealTool package, which extend the capability of the OpenFOAM to solve the rheological problems. Right. We test this one in a hyperbolic contraction. We would like to observe the behavior of the roly-poly model in the hyperbolic contractions. The reason why we choose this geometry is because this is the geometry which, the superior geometry, which is able to give a uniform extension rate along within the contractions region, which facilitate the calculations of the extensional viscosity. Right. This configuration can be observed from the figure 2 here. The whole domains of the hyperbolic contractions, which in this configuration, in this geometry, it produces shear at the wall and the extensionary response at the center line. So what we did is that we examine the extensionary rate as well as the stretch along the center line for 4:1 contraction ratio with different contractions length, just to observe how is this contraction length affect this quantity of interest. I mean the extension rate as well as the stretch here. So as a consequence of the symmetry, in 2-dimensional problems, only half of the symmetry is simulated, while for the 3-dimensional problems, a quarter of the flow domain is simulated. So this is my result for 4:1 contractions in 2-dimensional, where we impose pressure drops of 812 at the inlet. Here we can observe that within this contractions region, we are able to get fairly uniform extension rate for 2 different lengths here, where the longer contraction length, represented by the blue one, give you lower extension rate comparing to the short one. This is because of the geometrical changes that affect the velocity within that contractions region, which end up which does affect the extension rate as well. Just to be consistent with it, the stretch is also observed to be higher in the shorter contractions length comparing to the low one. We then extend our work in a 4:1 contractions for 3-dimensional problems. So where we would like to observe we would like to examine the presence of the side wall towards the extension rate and stretch of the polymer chain in a roly-poly segment. Right. So for this one, we consider, for 3-dimensional case one, we consider our channel to be square, and we impose the pressure drop of 512. And this is the result which compare the 2-dimensional and 3-dimensional, where my 2-dimensional we get fairly uniform extension rate, but we are not able to get the uniform extension rate for the 3D case one. This is because of the cross-stream flow profile from the side wall, which leads this to happen. However, we are able to get the identical extensionary rate for 2-dimensional and 3-dimensional if we let the channel of the upstream channel to be wide enough to avoid this effect. Right. At the moment, we are currently extend our work to include the polymer blends model, which is based on the Rowley-Poly model, containing both short and long chain, which can be visualized in figure 6a here, where we have the short represented by the red color and the long one is represented by the blue one, which later on, this leads to the theory of what we call as the double reptations. So these two chains length will lead to 4 different modes of interactions, which are, we have long interactions, long-short interaction, short-short, and short-long, which each of it are modeled with a couple Rowley-Poly equations. What we did is we implemented this model within the OpenFOAM, and we did some of the simulations on it to further explore the behavior of this polymer blends model. Right. We do not intend to describe the model in full here due to its complexity and because of the time constraint. However, we do some of the. This is our preliminary result where we do where we varying the volume fractions for the long chain as well as varying the volume fraction for the short one. This is what we get from here. From the 7a here, what happened to this extensionary rate is that increasing the volume fractions of L, we get the extensionary rate is reduced. This is because increasing the long fractions L will increase also the polymeric viscosity, which then make the flow will go slower and thus decrease the extensional extensionary rate there. Right. Okay. Right. Okay. So to conclude my work, so we have successfully implemented the Rowley-Poly model here, and our simulations show that we are able to generate the uniform extensionary rate in these configurations, provided that our 3D is high enough. And we also successfully implemented the polymer blends model here. That's all. Thank you.
Good afternoon, everyone. I'm Hani Al-Hamadi. I'm a second-year PhD student at Keele University, and my supervisor is Charlie Schneider. Today, I will be talking about the Newtonian models for vertical drainage free liquid fill. So, first of all, what are foams? Foams are gas bubbles separated by a network of thin liquid. And if we zoom on the thin liquid between two bubbles, we can see the middle section, which is called the lamella. And this lamella drains to the blotter borders. They are widely used in many applications, such as aircraft and automotive. And our interest is to understand how does it drain and how to control the drainage in order to make them alive for longer. So, and we also need to see the thinning rate in the middle section in order to keep them from collapsing. So here is our model problem. So we consider two-dimensional flow due to the drainage in vertical aligned thin liquid with two free surfaces, and the drainage evolves due to the facts of gravity and surface tension and viscous forces. So we make our model simple. So we assume that the drainage is suspended between two horizontal frames, and we also consider two Cartesian coordinate system, x and z, in the direction, in horizontal direction along with the film's thickness, and x in axis in vertical direction along with the length. So we assume symmetry at the center line, and we only consider the positive half of the film. At the free surface, we have the free surface, we have the normal stress boundary condition, which is proportional to the curvature. And we also assume that the liquid is pure. So we have zero tangential stress. There is no Brownian effects like surfactant and electric field or other physics. Finally, we have the kinematic boundary condition. So then we use the lubrication theory to reduce and simplify the Stokes equation and our boundary condition to derive non-Newtonian evolution equation. And then we use high resolution numerics to explore one-dimensional drainage, dynamic, and the thinning rate of the middle section of the film. So for background, Schwartz in 1990, he considered thin liquid with surfactant with same geometry. And he was interested to see the thinning rate in the middle section. And he found that the thinning rate to be t raised to minus a half. And Nair in 2001 considered thinning rate drainage from the lamella into the blotter border with surfactant. And he also found the thinning rate of the middle section to be t raised to minus a half. And then Brush in 2008 considered horizontal thin non-Newtonian liquid drainage into blotter borders. And he found that the drainage rate to be t raised to minus 2. So, evolution equation, we reduce the Stokes equation and the boundary condition using the lubrication theory. So, we derive a coupled of non-Newtonian evolution equation. The first one is the film thickness, and the second one is it's for the extensional flow speed. So, the second term in the first equation is the extensional flow, and we have the mu, which is the viscosity. Which could be Ferri, and the Ca is the capillary number, which compares the surface tension with the viscous forces, and the last term B is the bound number, which compares the gravity with the viscous forces. And the second, and this equation is coupled with the extensional flow equation. We have the first term is the viscous term, and again we have the surface tension and the gravity. So for our boundary condition, we have the zero flux boundary condition, and we fix the thickness to B1, and from there we can get the third derivative for H, which is the gravity over curvature. So for our non-Newtonian models, this is the leading order, extensional shear stress as a function of the shear rate, and when mu is 1, we have non-Newtonian. Power law implies that equation, and K is the consistency coefficient, and N is the power law index. So when N bigger than 1, we are considering the shear thickening. When N less than 1, we consider the shear thinning. So Ankró is the last model, whereas the mu infinity and the mu naught are the limiting viscosity at low and high shear rate. And lambda is just the relaxation time. So first of all, we'll see the result for non-Newtonian. So the first one is the left-hand side is the thickness. And we can see that it's, we initiated the model with a constant thickness of 1. At the top, we see the thin, it's rapidly drainage thins, and at the bottom is it's Belgium due under the gravity. And as time progresses, we can have longer and flatter middle section. So for the speed, we initiated the velocity with a quadratic profile, and we can see that the speed decreases everywhere as we approaches the steady state solution. For non-Newtonian, there is no much different in the thickness profile and in velocity between Newtonian and non-Newtonian. So we try to look for the thinning rate in the middle section. And we find that by looking at the maximum speed at late time and the corresponding point in H. So we found that the Power law, as N increases, as does the drainage rate. So, and we found the thinning rate in the middle section to be T raised to minus 2.5. For Corot-1, we found that as N decreases, the drainage rate will increases. And we found the drainage rate to be T raised to minus 2 for all N. But in Power law, we found that when N bigger than 1, the drainage rate to be T raised to minus 2.5, less than 1, T raised to minus 2. Just to conclude, model problem physically represent lamellar drainage into blue-top border. There is no much difference in the shape profile and the flow speed between Newtonian and non-Newtonian. The thinning rate in the middle section for Power law is T raised to minus 2.5 when N bigger than 1, when N less than 1, T raised to minus 2. And for Corot model, we found that the thinning rate is T raised to minus 2 for all N's. And Power law model is in physical because at the extension flow is at low shear rate. So the viscosity much stronger when N bigger than 1 than N less than 1, and Corot-1 is more realistic. Thank you for attention.
Any questions? Yeah.
Maybe I can pay attention. Did you consider surface tension?
Yes. Yeah.
In those pictures of the filament thinning, you show the filament thinning down to 0. Does your model, can your model handle the breakup of the filament, or does it?
We know it's not going to break because we do it numerically. So, no, if it's a break, we cannot handle it. Yeah.
Okay, thank you very much. I think it's lunchtime.